Okay, so the topic today is design patterns in Ruby. My name is Andy Maleh. I'm a senior software engineer at Eltropy, Canada. We're a debt collection agency that just graduated into not just that, but also we merged with a company that does conversational software for banks and credit unions. And we're going to be integrating our debt collection Ruby on Rails app with their conversational software. So we just merged with them a month ago, and I'm very excited about that. Our new name is Eltropy Canada. They're based in Silicon Valley, so we'll be visiting them in a couple of months, but we're their Canada branch now. And so the topic is design patterns in Ruby, and here I'm saying, who said dynamic languages can't have patterns? So I noticed that in the Ruby community, a lot of people have this myth or legend that Ruby doesn't have design patterns, or you can't do design patterns in Ruby. Like design patterns are only for older languages like Java and C++. But according to my work and my job, we apply a lot of design patterns all the time in our Rails app. And not just me and a lot of other coworkers. And they're a very helpful tool in enabling higher productivity and better maintainability of the code. So that's what I'll be talking about today. So before I get started, I just want to start with a pop quiz, like a quick pop quiz about design patterns. So who are the Gang of Four? And I'm going to give you three choices before you answer. Number one is a group of Communist Party leaders in China. Number two is a rock band. Number three is just a bunch of computer programmers. So who says it's number one? Nobody. Oh, that's the right answer. You win. There you go. Boom. And that's the rock band. That's their music, Gang of Four. It's actually a post-punk rock band from the UK. They sound pretty cool, actually. I actually listened to all their albums while building the presentation slides. So they're really fun. But yeah, I mean, to cover who the different... So these are obviously the Chinese Communism Party leaders. This is the band, and then these are the programmers that wrote the book Design Patterns. There's a book that brought this idea to software development. There's a couple of books, actually. There's another book by Kent Beck, which might have been Smalltalk Design Patterns, but they came up with just design patterns, elements of reusable object-oriented design. So something like that. So the Gang of Four is four very, very intelligent software engineers. I've actually had the pleasure of meeting Eric Gamma, this guy. He's a Swiss guy. I saw him at EclipseCon in 2006 when I was presenting there. So that was a pretty cool experience. I talked to him a little bit. So yeah, they came up basically with design patterns. So what is a design pattern? Design pattern is simply a reusable solution to a common problem encountered at the software design level of abstraction. So when people are building software, they start with requirements first, meaning what are the needs of the customers, and then they break them down into the general architecture, like, okay, what are we going to do? Are we going to do MVC? Are we going to do web services? Are we going to do what? So that's architecture. And then at a lower level is software design. Software design is when you're designing the different classes that you're going to build in code at the lowest level when you're writing the code. So design patterns help at that level. There's something else called architectural patterns that help with architecture. They're not the topic of this talk. There are books on that as well, different books. But this talk is about design patterns, which are patterns that help with coming up with the object-oriented classes, their relationships, and their collaborations between each other. So yeah, they were created by the Gang of Four: Eric Gamma, Richard Helm, Ralph Johnson, and John Villasides. I'm not sure how to say his name. It's inspired by the book. So originally, that whole idea of design patterns came from something outside of software. A book called A Pattern Language by Christopher Alexander, which was in relation to architecture of towns, buildings, and construction. So originally, the idea came from real architecture, not software architecture. And then it made its way into software design and software architecture. So what does a design pattern consist of? Design pattern consists of a pattern name. It describes what the pattern problem, solution, and consequences are in a word or two. So it's just like a sort of a handle just to remember what the pattern is. then there's a problem. What is the common problem that it's solving? So when do we need to apply the pattern and under what context? And then the solution, which is what are the design elements that the pattern provides in order for me to solve the problem? Design elements are usually like the classes or objects that are interacting with each other to solve the problem. What are the relationships between the objects? What are their responsibilities and collaborations? Last month I gave a talk titled Responsibility-Driven Design in Ruby, and it was talking about the basics of object-oriented programming. Here, design patterns assume that people, okay, they know now the basics of object-oriented programming. They're moving to something more advanced. But one of the basic topics of OOP was actually CRC cards. Has anybody heard of CRC cards? So that's an object-oriented design approach that basically helps programmers come up with classes gradually by taking a bunch of like white cards and writing a class name, like let's just say order, and then writing on the left side the methods of the class that matter the most. So for an order, usually you need the order total, calculation of the order total. Then on the right side, what does the order need to collaborate with in order to get its job done? So an order will need to contact order lines usually, and then order lines will need to contact products. So then you take a second CRC card and you write on it order line, and a third one, and you take a third one and you write on it product. So that I basically demonstrated this approach last month, the previous presentation. So this is basically talking about how design patterns build on this. So that's like the basis, and then design patterns build on top of it. So they assume that you know about this technique, or at least you don't have to know about CRC cards, but at least you know that objects, they have a name, they have to interact with other objects, and they have to have responsibilities. And as long as you know that, then you'll be able to understand design patterns. Finally, consequences, which is what are the results of applying the pattern? So usually it should solve a problem. That's one of the main consequences, is solving a problem. But also, what are the trade-offs that the design pattern introduces? Like it might, for example, simplify flexibility, but increase the lines of code that you have to write. So now you have to write a bit more code, but your code is going to be honoring the open-close principle, meaning you can add classes without much effort and without having to update or break older code. So there are trade-offs. It's important to think of the trade-offs. That's not always the case. Sometimes it's the opposite. Sometimes design patterns are such a good solution for the specific problem that you have that they're better than anything else. Like their trade-offs are actually very positive. So it depends. I'm not going to cover consequences in detail in this talk because this talk is an overview of all design patterns. I'm going to try to breeze through as many of them as I can. There are 23 design patterns, by the way, from the book Gang of Four Design Patterns. So, sorry, from the Gang of Four's book on it. So that's why consequences, if you want to learn more about them, read the book. The book is awesome. It's a very good book. So design patterns are divided into three categories, basically. Creational patterns. They abstract the instantiation process of objects, making a system independent of how its objects are created, composed, and represented. So these are creational patterns. The second category is structural patterns. They relate to how classes and objects are composed to form larger structures. So structural patterns are about making structures. And then behavioral patterns they concern algorithms, meaning behavior, and the assignment of responsibilities between different objects and communication between the objects in order to accomplish behavioral goals, meaning the goals of algorithms. So what are the benefits of design patterns? Like, why are we even studying this? They save time on solving already solved problems. Like, the whole point of having reusable solutions to common problems is if somebody solved the problem that you're trying to solve 50 times before, why are you wasting time reinventing the wheel? You could just apply a design pattern and solve that problem instantly. Once you master them, basically, or you don't even have to master them. Once you know them in general, you'll have an idea on how to apply them at work. I mean, that's how I learned them. I basically, I learned design pattern. I did a master's in software engineering in Chicago at DePaul University, and I learned design patterns mostly in that course initially. in one of the courses that I took. And then I started applying them at work. I was a full-time employee at the same time while doing my master's. So I started applying them at work, and gradually, bit by bit, I started noticing that they simplify my development techniques. Like I remember one of the first patterns I applied was called decorator, and it gave me a lot of flexibility in how to compose objects to solve different problems in a very flexible way. So yeah, that's a very good recommendation, is while you're reading the book or getting into them, it's good to start trying to find ways that work to apply them. So yeah, design patterns help improve maintainability when software behavior gets complex by adding structure that improves separation of concerns. So that's a very big thing. Like when people start getting their software, once their software starts becoming really complex, sometimes people end up creating God classes, meaning like, this one class that has 1,000 lines of code with a giant case statement and it's doing everything. That's like the opposite of design patterns. That's like why we have design patterns, because in that approach, you end up having to maintain too much logic in one file, and it slows down maintainability incredibly, and it forces me to scan through the file every time because it's a huge file. So design patterns is about breaking that file down and coming up with patterns that make sense intuitively so that you can quickly find the different files that are responsible for whatever you want to fix or maintain or add a feature to. Design patterns serve as a good software design communication tool for software engineers working in a team. So me and my teammates, I think of a problem, I'm like, this is the strategy design pattern. I apply it and I do a code review, one of my coworkers reviews my code and he's like, oh yeah, strategy design pattern, it makes sense. Then sometimes he uses the template method design pattern. That's a pattern we use quite a bit at work, and I'm like, wow, that makes perfect sense here. Like it really helped simplify the code and dried it up and made it more maintainable. So it's a very good communication tool between programmers once they've all learned design patterns. And then finally, they enable developers to honor the open-close principle to keep their libraries open for extension, yet closed for modification. This principle doesn't always matter, but there are times when it really matters. Like if I'm, in our case, in my job, we have a lot of payment gateways that we support. So we support Zoom Rails, payment gateway, Repay, Stripe, Nuvei, a lot of payment gateways. Every time we add a new payment gateway, we don't have like a giant case statement that we have to add one more case to for that payment gateway. What we do instead is apply design patterns and like just add a new strategy for the newest payment gateway. So that way our older code, we don't break it, we don't touch it. We just add one more class and it works and it fits in with the old code because it fits in with one of the design patterns that we apply. So that's the goal of the open-close principle, is to try to make the code flexible enough so that you can add bits and pieces to the code without breaking older code and having to change it. So let's get started. There are a lot of design patterns to breeze through, so I'm going to start breezing through them. So the first one is abstract factory. Basically, it's needed to create families of related or dependent objects without coupling consumers to creation details. So the solution for that problem is you write an abstract factory interface for related objects that need to be created as a family, and then for every family that you need to create of those objects, you create a subclass. So we use this at work. We have, I think I have it here on the slides. Let me just show you the slides. This is just the UML diagram for it, where we have an abstract factory, and it can build a series of objects. So think of it as, let's just say, there's, for example, I'm building a GUI toolkit, like a toolkit for rendering desktop development user interfaces. User interfaces always have things like window, button, text field, label, etc. So you can make an abstract factory that builds all of those basically elements for Windows. And then you can make a separate factory for Mac and a third factory for Linux. And every factory has its own implementation for that specific environment. But then now you have, if you want to extend, if you want to support Raspberry Pi, you can add one more factory. So it's a very flexible technique, again, for honoring the open-close principle, where you can manufacture related objects together under a theme where every factory covers a certain theme. like Mac, Windows, Linux. Or I worked at a company in the past where we had factories like that for real themes. Like we had one factory that was styling things with the color blue in a certain style for certain customers, and we had another factory that was styling things in a completely different way. That was a job where we were building a desktop app, actually, not a web app. But in my case, at work, the way we need this is basically we have to import spreadsheets of customers, and they could be either debtors with campaigns to collect debt from them, or they could be recipients with communication objects that will just send them an email and tell them, we just want to communicate something to you. We don't want to collect debt or anything. We just want to communicate like a new privacy policy or something like that. So we have two, so we need two basically, like we can build one abstract factory for generating those two objects of like debtors and campaigns, or recipients and communication objects. And then one of them is for debt collection, so debt collection factory, and the other one is info communication factory. So they're two different themes that are generating the same style of objects for different purposes. And that's just some code that's showing how it happens. Like this factory can create a service and a customer from a spreadsheet and a spreadsheet row, but then like this one will intentionally create only debt collection objects for the service and debtors for the customer, whereas this one will only create info communication objects for the service and recipients for the customer, because those guys are only going to receive a message. They're not going to have to pay or anything. So that's a quick example. Let's go to the next one. So builder is how to separate the construction of a complex object from the representation of it. So usually you need a builder interface that contains all the operations that you need to build an object step by step, and then you generate the final object. Another alternative is to create an abstract builder class and then have subclasses of it for different representations. So one builder can build an Excel sheet, another builder builds a CSV file, another builder builds a pipe separated values file, and all of them start with the same data at first, but then they generate different stuff. So this is a common example of builder. Is you have a house builder, it's got build walls, build doors, etc. So I can basically add as many of those as I need for the house. So let's just say every time you say build walls, it builds 4 walls, like it builds a room, basically. Every time you say build doors, it adds a door to a room. So you can customize the house any way you want by calling those methods as many times as you need. And then once you're done, you call the result. You grab the result. That's the final object. So it's a very flexible pattern, because by separating the construction from the representation, it enables you to very flexibly build many different kinds of objects from the same builder. Unlike as the basic abstract factory, which you have to subclass for every instance of that object. In this case, the same builder can build many different kinds of objects depending on which methods you invoke on it. So what's an example at work? Oh yeah, at work we have a builder. Actually, we have a multi-step form. We had a wizard, a campaign creation wizard. It walks users through like 4 steps, like building a campaign. Let me see if I get into the details here. Yeah, there you go. Step 1, step 2, step 3. And then finally, once the user finishes the wizard, it generates the final campaign. So yeah, there you go. Step 1, 2, 3. This one adds customers to the campaign. This one edits the message that's planning to send to the users. And this one configures the campaign send date. And finally, this constructs the campaign. This is loosely what we have at work. It's not exactly the same. What we have is a lot more complex, actually, but this is loosely what it is. So it helps us basically, we have one Rails controller that is receiving the step name after the user submits every step. And based on the step name, it figures out which builder method to invoke. And it dynamically invokes it and builds that part of the campaign. And at the final step, when the user finishes the last step, it generates the final campaign and stores it in the database. Again, that's loosely what we do. What we do is actually a lot more than that. But next pattern is factory method. This one is about having different subclasses build different objects depending on their needs. So factory method is like a mini version of abstract factory. Abstract factory was like this class that built many related objects for something. Factory method is like taking one of those methods only on an abstract factory and putting it on a normal class. And if a normal class has subclasses, every subclass might need a different type of that object, so they will just override that method. So, for example, we have, let's see, maze game, and if we override, okay, if we use the subclass magic maze game, then it builds a magic room, but if we use ordinary maze game, it builds an ordinary room, but the method name is the same. So they're going to have the same method for building a room, but different subclasses of this will build different objects. They call that a factory method. It's not really as fancy as it seems. It's just basically a factory method. But at my job, we have different, at my job we use this, We have payment processors for different, like I mentioned to you guys, we support Zoom Rails, Nuvei, etc. And each one of them needs to talk to a different payment API. So we have basically a factory method that builds the payment API differently for each one of those. So for Zoom Rails payment processor, it's going to build Zoom Rails payment API. For Nuvei payment processor, it'll build Nuvei payment API. So that's an example of factory method. You don't have to worry about taking screenshots. I'm going to post all the slides at the end of the talk, and I'll give you a link to them. So these are the APIs, for example, and then these are the classes that build them. So they have a create payment API, and here it builds a Zoom Rails payment API. Here it builds a Nuvei payment API. Very basic stuff. It just overrides this. It's not implemented in the superclass, but it's implemented on the subclasses. Okay, next pattern is prototype. There's a need to build a complex object a certain way with several variations. So what you could do is define a prototype object, because the object is very complex to build. It'll take like many lines of code to build. But what you could do is if you need that object many times in your software, but all of them will start with the same prototype, you basically create a prototype that has everything you want in it, and then you clone it, and then you add more to it after that. By the way, JavaScript adopts the prototype pattern for its object instantiation implementation. So in JavaScript, the real JavaScript doesn't have classes, it has prototypes. So you have prototype inheritance where instead of having a class hierarchy for inheritance, you have prototypes actually in JavaScript. So now ECMAScript recently hid that. So they offer now what looks like a class, but behind the scenes, as far as I know, it still generates prototypes. Doesn't matter, but it's an interesting fact that they use a design pattern in JavaScript. So here's the prototype, and prototypes of an object that a client needs. Doesn't matter, but you might have different clients, like different archetypes. Let me see if I have an example here. Yeah, like a user, an admin, a visitor, and they have different needs. So you can generate prototypes for them and continue from there. That said, the place where every Rubyist uses prototype nowadays is FactoryBot. So FactoryBot is actually a prototype pattern library too, for testing. So for testing, almost everybody uses this, and basically that's the older version of it, but either way, it's basically, this is a prototype. So here I'm defining a user, and the prototype of it is going to be John Doe, not an admin. And the admin version of it is going to be, admin user, admin true. So these are two different prototypes. So that's pretty much what FactoryBot is. Who here uses FactoryBot? Yeah, I assume so. I mean, a lot of people use it. We use it at work. Singleton is needed when there's a need to ensure that only one instance of an object exists in the entire system. So the singleton class controls access to instantiating objects to ensure that no more than one instance is created. And if one was created already, it'll just return it. So normally, this is made private. That's why this is a minus. So you cannot instantiate this class normally, but you can call get instance, and it'll always give you one instance of it. So this is needed. What's an example? Like a company serves one country only. I mean, my company was that way at first. When we started, we served only Canada for a number of years, for like 4 or 5 years. There was no point of generating a lot of like country objects because like it was mostly just in Canada. So when the code is smaller, often you want to take advantage of that and write simpler code until you get to the need where you have 2 countries or 3 countries or more. So if you have one country instance in the entire system, then you can just make it a singleton basically. and prevent the company new, I think I meant country here, but I wrote company, I don't know why, but either way, let's just say there's one company, one client. That's also a common pattern, case, actually. It's when startups begin, they have one client often for like 6 months or even a year. So if you have one company, you're going to make one and it's going to be a singleton. Now, Ruby gives you something called singleton library. So you can just require singleton and include the singleton mix-in, and your class becomes singleton automatically. So if I show you the manual way of doing it, I had to take the new method, make it private. So I overrode the new method and made it private. It doesn't do anything else, it just calls super, the original implementation. And then here I created an instance method, and it basically will check if there's an instance class variable. If there isn't one, it'll basically create a new object. If there is one, it'll just return it. That's it. So that's the manual way of doing singleton. That's how we did it in Java back in the day, but in Ruby we don't have to anymore. We could just do this. Ruby gives you singleton out of the box, from like included in Ruby, pure Ruby with no library, like without adding any gems. We use this at work quite a bit actually. We have a few singletons at work. So yeah, we just generate a singleton like that and we use it. Trying to remember what we use it for at work. I know we have a few singleton. One of the key ones I just remembered, we have a logging library, and it gives it, yeah, exactly. We have one logger. There you go, one logger. Yep, exactly. So structural patterns. So now we're going to move into the second category of patterns. So adapter. So adapter is basically if I have an existing object, object A, with a particular interface, and it needs it to interact with another object, object B, that requires a different interface, then you can create an adapter that wraps object A to make it adapt to the interface of object B. So to show you code, it's more understandable if I show you some code. So we have a client and it needs to talk to, let's see. Okay, so the client is expecting this interface with operation method, and then I have another class that does the same kind of work as this interface. Unfortunately, though, it has a different name. It has specific operation as the method name instead of operation. So what we have to, if I want to make the client use this new class, I'd have to adapt it first. So I can wrap it with an adapter class that has an operation method that matches that exact interface, and it also extends it. And then it can call the adaptee and invoke the specific operation. So yeah, that's how this works. So a real example is, I worked at a company in the past where we had this problem where we had an authentication library and it had a password authenticator by default, but you can also add your own authenticator classes. And we were integrating with an SSO solution. Let's just imagine Acme SSO Authenticator, but it has a login method instead of authenticate, which is what's expected. So we just had to adapt it. It was that simple. We built an adapter like Acme SSO every auth authenticator adapter, and then it had an authenticate method, but that one delegated the work to the built-in login method. So it's just a very simple example. This problem comes up every once in a while, like adapter, where you need to adapt stuff. Like one big example for it at my company, I just remembered, is we have often models that we want to render in the view, but the view is needs to normalize and adapt the data a bit before it renders it. So like instead of showing, for example, first name space last name, it's going to show last name comma first name or stuff like that. So it has to massage the data quite a bit before it displays it. So then what we do is we put a layer in between the model and the view. We basically put a presenter, and the presenter is just an adapter pattern. It basically will adapt the model to whatever the view expects, and it'll present what the view wants. So that's, presenter is a form of adapter. It's basically adapting a model for presentation. Okay, bridge. Bridge is a pattern where you need to implement abstractions in different ways or using different libraries. I actually just gave you an example of this earlier. So like I mentioned, if you have a GUI toolkit and it has window, button, text field, label, you might have three different implementations of it. The Mac one, the Windows one, and the Linux one. That's how Java built its own Swing library, for example. That's what they do. So Bridge library solves this problem. So basically, you can decouple the abstractions from the implementations. One way of doing it, I believe that's the way Swing is implemented in Java, is basically you make the abstractions use lower level methods to build their data, and then this lower level methods can be implemented in multiple ways as implementations. So I mean, to give you an example, let me show you an example. Yeah, here, like this one is from the book of the design patterns book, by the Gang of Four. Is you have a window, and to draw the window, you need to draw text on it, and you need to draw a rectangle. And the rectangle needs to invoke 4-line draw methods. These are the low-level methods that are needed to basically build a window. Is those like drawing a line and drawing a text, basically. So what you could do is basically the window can have different abstractions. Like you can have a window with icons. You can have a window that's transient, meaning a modal that will go away after you click an OK button or something like that. You can have different versions of window. They're different abstractions. But all of them are implemented using those low-level methods. And that's the bridge. And that ends up decoupling, and also that's the bridge here. And they have a reference to the implementation, and that decouples them from the inner implementation because all the implementations have the same interface, which is the low-level methods. So the window will draw itself using those methods without caring how they're implemented. But then on X Windows, on Linux, you can have one implementation. On PM Windows, they have a different implementation. So you can vary it by... you can vary the implementations for the same abstractions. So that way you can have the abstractions grow independently of the implementations and vice versa. It's a very advanced pattern. You don't need this every day. This is a very complicated pattern, but it could be very useful every once in a while. Often in user interfaces. So yeah, so for another example, like I have a user interface that renders also widgets like windows, buttons, etc. But it's gonna build with the same exact Ruby code. You can render the app as a desktop app or as a TUI app, textual user interface, meaning curses, for example, on the command line, or as a web canvas, for example, in a JavaScript using Opal Ruby, which lets you run Opal Ruby code in JavaScript in the browser. So this one so basically you can decouple the drawing of those abstractions by providing the methods that they need, like draw line and draw pixel. And after that, you can have different implementations provide those methods. So it's almost the same example I just showed you, but like a different variation on it. So these are the abstractions, label, text field, button. But then these are the implementations. I have a platform implementation that draws pixels and lines a certain way, a desktop canvas one, a TUI implementation, and a web canvas one. Actually, sorry, this is the interface. This is the superclass for all of them. That's why it says here not implemented. But that's pretty much it. Composite is basically how to compose objects of other objects while having parent objects and child objects share common behavior. So this is like building, for example, a tree. A tree has parents and it has nodes. Nodes are the children. Nodes cannot be composed of any more nodes, but parents can be composed of can have multiple children underneath them, meaning multiple other nodes underneath them. So define a child object superclass and a parent object superclass. That's the solution. And then make the parent object superclass extend the child object superclass because the parent is also a node. That's the key thing about it. And also the parent not only is also a node, it has a composition relationship to node. It also owns nodes. So a parent has children, but it also is one of the children. It could be a children to another parent. So that's what the composite pattern is. So we used this at work recently. We had a rule engine. We built a rule engine where you can nest rules within rules that were building Boolean expressions, with like and or and stuff like that. And they were needed by certain clients actually of ours to build data for, I'm trying to remember what it was. I think it was data for importing debtors into our system. They needed to use some data from a spreadsheet and compose rules and use those rules to normalize the data, if I remember right, and generate some new fields that they would add as metadata to those new debtors. you don't have to know all the details, but the key thing is that we had rules that were composed rules. So like if you had an expression that's an AND expression, it's composed of two statements that you're ANDing. So that's kind of like the parent that has two nodes. Whereas if you have a final expression like a child, that's basically the value, that is just a node that's a child, it's not a parent. So again, here we have all of them could be thought of as something. Here they're calling them components, but in the other case it was called, might have been rule, I forgot what we called it, maybe rule node or something. And then, so you have the leaf, which is usually the node, and then you have the parent, which is the composite. And the parent can add or remove leaves from itself, but so it has a composition relationship here, but it also considered one of the components, meaning it's kind of like the leaf. Again, this is a bit of an advanced pattern, but it comes up every once in a while. Like if you have a website that's representing books, books are basically chapters that are made up of sections that are made up of pages. So chapters and sections are parents, pages are nodes. So that's another example of it. That's how you implement it. You have a node, you have a parent node, which is also a node, but also it hasn't, this is basically a composition where it also has children that are nodes. And then you can have different kinds of it, chapter, section, page. Basically, a chapter can only include sections. In this case, they have, like the implementation would have a bit of logic that would ensure that, and sections can only have pages. Okay, so decorator pattern is basically object capabilities need to be enhanced at runtime without modifying the object code, nor relying on inheritance to honor the open-close principle. So you can create a decorator object that wraps the original object and adds extra capabilities, offering more flexibility over creating endless inheritance hierarchies. I'll give you an example of this. Actually, let's jump into the real example here. So in a car racing game, you have a car, and it has acceleration capabilities, and it can move, but the car can be enhanced with upgrades. So you can add turbo, you can add like a turbocharger, you can add performance exhaust system, you can add a long tube exhaust headers. While, by the way, I'm not an expert on these things. I had a friend that was obsessed with like modding cars and stuff, but I personally don't do it. But while being able to combine upgrades in any combination you want. So like, for example, you can add turbo and this at the same time, or add turbo and that at the same time. So if you were to use inheritance hierarchy, you're gonna have an explosion of classes. That's not a good solution. You're gonna end up with like this version or this version or this version. You're gonna end up with 6 subclasses or maybe even more. And every time you add one more upgrade, you're gonna have to add so many more combinations. So that's why subclasses are not a good solution. So in this case, we use decorator instead. Subclasses also compose these things at compile, or sorry, not compile, at code time, whereas decorators compose things at runtime, so they're more flexible. So meaning you can have a car at runtime, and then the user can add upgrades to it at runtime without restarting the app or anything, and then they can start the car, and now it's upgraded with decorators. So if we were to look at the code, we have a car, it moves. It doesn't have any implementation for the basic car, but we have a Dodge Charger car, and this one moves with like the speed of adding a 0. So assume that the move method gets called 30 times a second, like kind of like with games, you're rendering it 30 frames a second. So it'll move it. It'll move it 0.1 miles only for a Dodge Charger car, and but if you add the turbo decorator, it's going to double it. It's going to basically move. It's going to call super, meaning move it with the basic engine, and then it's going to do turbo move on top of that. So it'll add one more 0.1 to the position. So that means it moved it double. So that's like doubling your acceleration. So this is the car upgrade decorator. That's a super class. It basically will have a reference to the car, and the move method will simply invoke the move on the car. That's how decorators are implemented for the super class. But then every subclass will change the move and do something different with it. Normally they'll start with the super to invoke the default behavior first, and then they'll add more on top of it. So then if I bring an performance exhaust system, it's going to add 0.05, and this one's the long tubes exhaust headers, we're going to add 0.02. So if you combine all of them, you're going to get a much bigger number. So here's an example. If I have the car alone and I move it once, it's going to give me 0.1 miles. If I turbocharge it, it's going to move it 0.2 miles. And if I add all of those together, see, I added all of the decorators together. That's the nice thing about decorators. You can add as many of them as you want. And now it moved 0.27 miles. Those things added even more acceleration to the car. So that's what that is. It's a very flexible pattern. Facade is basically system objects that are, okay, so the problem is we have system objects that are too low level or complex to enable a consumer to interact with them conveniently. So you can, instead of having the consumer deal with all the model layer that's very complex and has many objects, you can build one class that's a facade that enables consumers to just talk to the facade and do everything. So this is, for example, we have a compiler. So let's just say, forget the compiler. We have a stream class, a scanner, a parser, a token, a symbol. If you want the consumer to deal with all of those at once, it's like so much complex work, and it has to have internal knowledge of all of them. So you don't want that. That's not convenient. What you could do instead is abstract all of them away and hide them behind a compiler, and the consumer would just talk to a compiler until it compiles, done, and it does everything. Like the compiler has the intelligence of what to do with all of those objects. So that's what a facade is. It hides complexity. So for example, I built a snake game a while ago, and it's got a snake, and the snake is made up of vertebrae, and then there's an apple, and the thing is, when you I only care about starting the game, pausing it, resuming it, seeing the score and seeing the high score. I don't care about like dealing with the vertebrae and the snake and the apple. So what you could do is build a game object that's a facade. So this is the game that I built. I built it with Glimmer DSL for libui, which is a library, an open source project that I built. It also won a Fukuoka award by Mats, by the way, 3 years ago. And this one, basically, if I click on the implementation, there it is. So it's basically, it does have like an apple and a snake and stuff like that, but you don't have to deal with it. All you have to do is start the game, pause the game, or resume it, or you can toggle pause if you want. And then you can call the score and high score methods to see the score. So like if we go back to the game here, notice how the score is increasing as the apple is being eaten, see 150. So basically 200. So we have a view that sits on top of that class, and the view doesn't have to deal with all the like the apple and the vertebrae and all of that. It just talks to the facade, and it handles everything it needs for showing us stuff on the view. So that's what facade is. Flyweight is basically, there's a need to instantiate a lot of objects with repeated attributes and dependent objects, wasting memory and performance. So what we could do is share objects that have equal attributes by caching them and avoiding their instantiation if they were instantiated before, returning existing cached objects to conserve memory and response time. It's pretty basic. It's just a fancy name for caching, honestly, flyweight. It was one of the earliest versions of caching, I suppose, but it was a pattern back in the day. People now do caching all the time, but basically, yeah, there it is. Like here, it's seeing if the object exists based on a key, then it returns it, otherwise it creates it. And you can make different objects flyweight. So I have a real example here. So my library, Glimmer DSL for SWT, which builds desktop apps on top of JRuby. That's a different, I have set, by the way, 8 open source projects for building desktop apps on top of 8 different toolkits. I support everything in Ruby that's available in Ruby. So SWT is one of them. It's on JRuby. This one has fonts and colors that are often created in the same app multiple times with the same exact values, like let's just say 12x solid black or whatever, like for the font or color. So if you're doing that a lot, you don't want to waste memory. You could use the flyweight pattern. I actually did do that in my project. Like my font proxy class is actually flyweight. See, it even has the word flyweight in it, but when I create it, it checks those arguments, and based on those arguments, if something existed before for them, it returns it. Otherwise, it generates a new font. So that way, I don't waste memory. Same for color. Color is handled the same way. It's also flyweight. But yeah, it's just a fancy name for caching. Proxy is basically there is a need to interact with an object indirectly by connecting to a surrogate object instead of the main object that facilitates interaction with the original object. So create a proxy object that facilitates interaction with the original object, while hiding it and optionally augmenting access to it with extra features like caching, like security, failover, retriability. So there are different applications for proxy. There's the basic application, which is you have a proxy in memory for another object in memory. So I have a real subject here, but for some reason, I don't want people to deal with this object directly. So I can provide a proxy, and the proxy hides that real object and lets the user interact with this instead. I actually use this pattern also in Glimmer. I'll show you where. Basically, yeah. Actually, it's not me. JRuby uses it. I use it and JRuby uses it. So JRuby lets you talk to Java from Ruby, which is awesome. But the way they do it is they use the proxy pattern. So they take Java objects and they give you Ruby proxies for them. And then you can call methods the Ruby way. So I can say self.layout equal instead of saying set layout, which is the Java way. So JRuby will automatically, it has intelligent proxies that will auto-convert the Java conventions to Ruby conventions. So that way you can just write Ruby while using all the libraries of Java at your disposal, which is awesome. That's how I built Glimmer DSL for SWT, because that one is using the Eclipse SWT library, which is a Java library for building GUI. So the other kind of proxy is what we use on the web. So on the web, often we might have an object here, and then there's a proxy that's talking to it over the network. There are remote requests. So this is like RMI pattern or like GraphQL. So GraphQL is like kind of like it's giving you a proxy to a database hiding behind the server, but you're talking to it in JavaScript on the front end as if the database is with you in the front end, but it's not. So that's like the proxy pattern as well. In Java, there's something called RMI that lets you do that for desktop apps as well. You can put a server in one computer on the cloud, and then put another computer somewhere else that has a desktop app, and it can talk to the server using RMI with proxies. So yeah, I also use it in Glimmer DSL for SWT for other reasons. I proxy SWT GUI toolkit objects and hide them behind Ruby objects as well, but let's not get into that for now. So, okay, we finished the first two categories. That's pretty good. So we're finally at the last category, behavioral patterns, which is the most important category in my opinion. This is the category I use, the patterns that I use the most at work. Chain of responsibility is how to decouple a sender of a request from its receiver so that it is not known which object from a collection of objects will be most suitable for handling the request. So kind of like fire and forget. Like instead of, like, let's just say I want to send a request that could be handled by one of 10 objects with different trade-offs. I don't want to deal with that logic myself. I just want to tell them, like, handle this request and give me the result. That's it. And what you could do is take the objects that can all handle it and let them figure out which one is most suitable for handling it by putting them in a chain of responsibility, which is kind of like a chain of command. And you start from the top, and they're prioritized. They have an order, and the first one will look at the request. It'll be like, can I handle it? If it cannot, it'll send it to the next object. If it cannot handle it, it'll send it to the third, all the way till it reaches an object that's suitable. This pattern is very rarely needed, but I used it actually to build, again, Glimmer DSL, because the Glimmer DSL is a very complex thing. So DSL means domain-specific language in Ruby. And when I have a domain-specific language and I'm building GUI, it's got controls, meaning like a text box or a label or button, but it also has properties, like some keywords in the language are properties of those elements. So that's a different expression. It's a different kind of thing to handle. And there are also things that are listeners, and like there's 10 categories of things that could be handling the request of a keyword that is invoked in Ruby for the Glimmer DSL. So instead of the traditional old way of doing it is you would have a giant case statement that handles all the different cases in one case statement. But that's the whole point of design patterns, is to break away from that and not do that. So the way to break away from it is to use their chain of responsibility pattern. So for every expression in the DSL, I have a different object that can handle it, and they're all chained in a chain of responsibility, and they're ordered in importance. So if I click here, for example, this is the DSL for Glimmer DSL for LibUI. This is the entire chain of responsibility. So first it checks if it's a listener. If I write a keyword and it starts with the word on, like on clicked is always a listener. So the listener will immediately recognize it and be like, oh, I can handle that. And it'll handle it and it'll generate a listener in Ruby. If it's not a listener, if it's a different word like text field is not a data binding, it's not a property, it's not a content, it's not a string, it's not an operation, it's a control. So finally, this is the one that's going to handle it. So it's important to order them in the right order, because you don't want objects to grab things that are not theirs also. Sometimes you push things below when you know they're not going to get reached most of the time, like shape. We rarely use shapes in Glimmer. Shapes is a more advanced feature. So anyways, that's what, by the way, this thing also, if I'm not mistaken, this is how you implement virtual machines. So virtual machines, as far as I know, are basically chains of responsibilities of operations. So think of every one of those as an operation, except in Java, the bytecode is the different expressions. So here, the different expressions I have is listener, operation, control, whatever. In Java, bytecode is different. It's like the Java bytecode, which is like an add operation, a divide operation, etc. Stuff like in the Java domain. So that's how you build virtual machines, as far as I know. So yeah, design patterns are very flexible. They give you a lot of options. Command. So command is very common. It's how to divide work that the user needs to execute in any arbitrary order while providing support for undo, redo, if needed. It's not always needed. So implement every small unit of work needed as a command object. And that gives you the flexibility to orchestrate multiple commands behind, a command will be talking to multiple objects behind the scenes. That's just, commands usually hide operations that are orchestrating lower level models, but every command can be sequenced in any order you want. That's the benefit of commands. You can sequence them in any way you want. So a real example of this, without getting into that, is I built a Ruby IDE actually called Gladiator using Glimmer DSL for SWT, and it needs to have like keyboard shortcuts like any other editor, like Vim or whatever, or VS Code or anything. So every shortcut is a command. So I treated every shortcut as a command, and for example, I have it open actually. Yeah, there it is. So like I can basically go here and like this is a command, this is a command. I can move this line like that. I can move this like that. So and then I can do undo, redo. So this is undo, this is redo. So basically, this is command pattern. That was implemented with the command pattern. So usually commands only have one method that's called execute. In Ruby, the way they do it is they call it call to make it act as if it's a proc or a block. But if you want undo support, you need to add a second method called undo. So that way every command can be executed or undone. And once you undo it, if you execute it again, that's like redo, basically. So that's what undo redo is for command pattern. And yeah, it's a useful feature, but it could be overused. I've seen a lot of Rails developers overuse it and build commands for no reason. The problem with command, the trade-off, is that you build objects that are too small. So if you have, it's only useful if you want to sequence them in an arbitrary way. But if you don't need to sequence them, if you're just building commands when you could have like put all the methods on like one object that is more cohesive and representing what those methods are, that's a better way of modeling the object than using command pattern. So command pattern is not always a good solution. I know in Rails sometimes people call it service object or service pattern, but it's overused. It's usually you want to use it with balance. You don't want to overuse it. Interpreter is basically a pattern for interpreting a language of expressions by breaking them down into a grammar of granular expressions. And you divide the grammar of the language into expressions, and then you have expression handlers for every expression. So yeah, you break an expression down into different kinds, and then you handle it with different handlers. So again, this is how I build Glimmer DSL. I combine multiple patterns, basically. I have interpreter, I have chain of responsibility, and I have, I forgot what, there's one or two more patterns that are used in it as well. So this is needed because I basically combine chain of responsibility with expression handlers. So I have an interpreter because you have to interpret the DSL, but you interpret it by using a chain of responsibility. So that's how Glimmer is built. So then you have a listener expression, a control expression, property expression, And like if I go into one of them, let's go into the control one, just as an example. So in order for something in the chain of responsibility to know if it can handle something, you need an interpret method and you need a can interpret method that will figure out first if it can handle it. So this one will just check, does this keyword exist as a control proxy, or as a control, meaning, does it exist as a control, as a libui control? If it exists, then yes, it says I can handle it. If it doesn't exist, then it cannot handle it. Once it confirms that it exists, then it processes it, and basically it creates a control. So that's how it works. It's that simple. Nice thing is it's a very small object. Like that's the nice thing about design patterns. They divide the code in very small units that make them more maintainable. Okay, iterator is how to iterate over elements of an aggregate object, like a complex object, in different ways. So you might want to iterate from beginning to end, or from end to beginning, or like you can iterate in any order you want. Like you can build iterators for any kind of iteration you want to do. So often, I'm not going to get into that. I think it's, well, I mean, the only thing to look at here is that usually iterators have a next method and has next. It's kind of like in each iterator in Ruby. So Ruby has iterator, but not as an object, as a method. So you can, if array has an each, and every time you go through the block of the each, it's going to go to the next element automatically. So that's an example of a method version of iterator, but here it's talking about class iterators, because class iterators are needed if you need more complex iteration than just each. If you need to iterate in some weird special order, like you need to iterate through the most important customers first of a collection to the least important customers, for example, or something like that. So you can build different iterators, but more importantly, it's used more for trees. So if I have a tree of elements, you can do depth first search algorithm as an iterator, or breadth first search as an iterator. Are you guys familiar with those algorithms? Yeah, so so the nice thing about iterators is you can build them as two separate classes, and if you think of other iterators, you can also add them as a third class. So it gives you flexibility of maintaining the code cleanly in different classes. So I use this in another Glimmer library that generates XML, which is a library that I use in Glimmer DSL for web, the one that just won an award last month for generating HTML for web pages. So this library uses a depth-first search iterator in order to generate the HTML from Ruby syntax. So like, for example, the Ruby syntax, I'll show you what it is. This is the Ruby code. Like I have code like this. Like I have a div, there's a section within it, there's a new to-do form, to-do list, to-do filters, etc. All of this maps to this. Like I have here a to-do list. So it rendered it. So that library rendered it, the one I just mentioned. Basically, it iterated through the syntax that I just showed you, and it did depth first search, and it basically spit out all that HTML that we're seeing right now on the screen. So yeah, patterns are amazing. You can build awesome stuff with them. Okay, next pattern is mediator. So there's a need to decouple multiple objects from each other while orchestrating a particular piece of work between them. So introduce a mediator object between them. Sometimes you get into this situation. I've had it at work a few times. I'm sorry, it's already 8 o'clock, but there are only a few patterns left. Sorry to keep you waiting. But I've had this situation at work a few times where we have two objects that are both talking to each other. And it's a frustrating situation because they're both dependent on each other. They have bidirectional communication, and they become very coupled to each other. And if you change one, sometimes that causes problems. It's not always a problem, but there are times when it complicates maintainability. So one way of handling this is you would introduce a third object that's a mediator, and it talks to both of them and handles the work between them without them knowing about each other. So it decouples them basically. And it has a unidirectional relationship between them. Usually in software, bidirectional relationships can be problematic sometimes, whereas unidirectional relationships are not problematic. They result in more maintainable code. So here we have a mediator that's talking to these two objects to facilitate work between them. So an example of this is work associated with processing an order requires orchestration between many objects, an order, a payment gateway, an address service, etc. So many things. So you can introduce an order processor object which is a mediator that will basically handle the work of orchestrating all of these together. So there's a lot of overlap between this pattern, I don't know if you notice, and command pattern, and also facade pattern. Facade is similar, but facade gives you a whole interface of multiple methods that can do things on those objects that it's orchestrating. Mediator could also do that in a way, but I think mediator has a different goal, which is decoupling, whereas facade has the goal of simplifying. They're very similar. Honestly, sometimes I mix them up. So yeah, similar to facade and command. Command, the difference between this and command is command usually has only one method. It always has one method. But sometimes you want to put multiple methods, so command is not the right choice. Next pattern is memento. Memento is just a fancy name for serialization. But to get into it, there's a need to externalize an object state without violating its encapsulation to save it in order to allow restoring the object state later on when needed. Introduce a mediator object. I think I meant memento. Sorry, my bad. That is responsible for orchestrating the work between multiple objects. This feels like a mistake. I copied this and pasted it without changing it. Okay, my bad. But yeah, what I meant is you would introduce a memento object, and basically the object that needs to save its state can spit out its own memento, meaning a version of its data that is ready for saving on a hard drive or something, and then later it can actually consume it and load the data into itself. So it's a useful pattern, but in Rails we usually use serialization libraries for this. We just use active model serializers or fast JSON API to save restore objects between backend and frontend, like when you're transferring data between backend and frontend. So that's one example for using serialization. And often we use JSON as the format for the memento. But here, like the pattern when it originally came out in the 90s, it was like obviously there was no JSON back then. They just had their own, like, you can invent your own basically textual serialization format and just basically save all the attributes of an object in a memento. So yeah, we have an originator object, and then you can save a memento from out of it. The key thing about this is it was more useful for statically typed languages like Java and C++ because you wanted to protect the encapsulation of the originator. So one anti-pattern in Java that's very common even today is basically you would have an object that's in not order. That's user, and user has first name, last name, email, all of those fields, and they're all exposed. And if you have everything exposed, none of them are encapsulated, basically. So in that case, memento is almost useless. It's not needed. But the case they're trying to deal with here is sometimes you might have let's just say a car object, like I showed you earlier, and it can move. But the details of the car engine and how much acceleration it has are completely hidden from you. In that case, let's just say you decorated the car and you want to save the decorations as a memento, you'd have to, that's internal state to the car that's not exposed. For example, if it accepted the method that applied decorators on itself directly instead of externally, that would be an internal state. So then then it can spit out its own memento that knows about its own internal state without any other class outside of it knowing about the internal state. So that was the goal of this. I think in Ruby it's not as important because in Ruby state is not really that protected anyways. You can even invoke private methods, so whatever. It's still good to know about though as a pattern. It reminds you that you want to serialize an object and then deserialize it. In Ruby, by the way, Ruby gives you other solutions for this as well. Not just Rails gives you active model serializers, and Ruby gives you Marshall and YAML. So when I build desktop apps and I need to save objects, I've used YAML and Marshall before to do that. Marshall can convert any object into a serialized version, and YAML converts it into YAML. YAML is actually better. Anyways, either way, they're good serialization options in Ruby. Observer pattern, probably everybody knows it. It's a way of performing work outside of an object's responsibilities whenever the object state changes. So instead of coupling an object state to some pieces of work that are outside the object, you can just add observers and have the observers do the work externally without the object being modified to do that work itself. So the object becomes observable, and then you can add observers to it. And once its state updates, the observers are notified of the changes. So this is very common in Vue, like in MVC, basically, because the Vue is monitoring the model or controller for changes and then reacting. So this is, that's what observer is. We have an object here. It can have an observer collection. You can add to it as many observers as you want, but as soon as something changes here, it's going to notify observers, and then observers are going to run an update method that will do their work. Different observers do different things. For example, if I have a real example, like I can have an order is going to change its state. For example, when you first create the order, it's a new order, and then it's a verified order. Once we verify that it has the correct data, and then validated, and then ready to send, for example. And then with every change, you can have observers observing that state, and as soon as something happens, see, subscribe to state transitions, and I can pass an observer to it. And as soon as that happens, you can have an email order observer that would basically, as soon as a state changes, it'll email the owner of the order that the state changed, and they'll know that, okay, your order is now ready to send. We're going to be sending you, you're going to be shipping you your order, basically. So this is an example of using the observer pattern. So, okay, state pattern. State is basically an abstraction. Okay, so the problem is that we have an abstraction that transitions through multiple states, kind of like an order, and behaves differently under each. So if it's a new order, it's not ready to send. And it will not email users, let's just say. But it will not email users until it becomes ready to send, for example. So it'll have different behavior in different states. So if you want to handle that cleanly, like the dirty way of doing it is you would put all the logic in one class, which is the order class. A lot of people do that nowadays. But the cleaner way is to apply the state pattern, which basically will divide every state into its own class. So you're going to have a new order state, a validated order state, ready to send order state object, and every object will have its own behavior. And then this will delegate its work, the main class, the order, will delegate the work to the state to handle the work. So let me show you some code. So let's just say, I mean, I worked at a company in the past that had orders that started new and then became, I think I meant verified, then shipping and then processed. And then, they could be also inactive. They could become inactive. So yeah, developers had tons of conditionals in the code. That's how we had it before doing the state pattern. And then I basically encapsulated the behavior of every state in an order state object, subclass. So there's an order state superclass, and then there are different subclasses for every state. So there's an order state unverified. It is unverified, okay. Order state shipping, etc. So this one says the ready to ship method returns true for it. This one returns false. And here, when you transition to the next state, it's going to verify the payment, and if it's verified, it's going to ship. Otherwise, it's going to mark it inactive. And this one is going to basically confirm the shipping address, and if it is ready, then it's going to process it. So either way, every state object then will, so basically it's a way of conquering dividing complexity. You would divide it into multiple state objects, and every state object will have its own logic that's focused only on that state. So it's a way of, again, it's a way of dividing thousands of lines of code into multiple files where every file is 100 lines of code only. Strategy is very similar. Strategy is similar, but it doesn't involve state. It's so you need to customize behavior with multiple variations at runtime by setting a strategy. But you can encapsulate each behavior in a strategy object. Again, there's an object that can delegate an algorithm's work to a strategy, and then the strategy will do different things based on the strategy. So we use this at work for the different payment methods that we support. We have a strategy for Visa, for credit card payments. We have a strategy for ACH debit card payments. We have a strategy for a third kind of payment, like Apple Pay and also in Google Pay, for example. So we use this pattern for that. It's very useful for that. It divides different pieces of work into different strategies. So it makes the code not have so many conditionals in one file. It ends up dividing the logic across multiple files. So it makes things more maintainable. Like, yeah, credit card payment strategy, cashier's check, PayPal. That's what I was talking about. So yeah, template method. So yeah, we only have 2 patterns to go. We're done. Template method is an algorithm needs to be executed with the same general steps, but for some of the steps, you might have variations depending on which subclass of your class is executing the algorithm. So you might basically have a superclass, an abstract class, that has one method that has a general algorithm, but some of the methods in that algorithm, they're called hook methods, they're going to have different implementations in different subclasses. So that's a way of basically having a general algorithm that can also be customized in certain subclasses. It's a bit complicated to explain at the end of the talk, but yeah, like for example, I have here some common work, like those 3 dots are common work across all subclasses, but those primitive 1 and 2 are overridable. So then this subclass is going to override primitive 1 and 2 and do something different in them. And subclass 2 is going to do something also different. So that's what, it's a very flexible pattern for customizing algorithms while also sharing the common algorithm code. So we do that, we use this pattern quite a bit at work. It's very useful, very, very helpful. Yeah, like we launch different campaigns that have to do a lot of things in the algorithm. They have to build a campaign activity and set up recipient objects and normalize data. All of that in general is the same, except that we need different types of campaign activities and recipients based on different campaign subclasses. And that's where template method comes to the rescue. So that's pretty much it. There's not much time to cover this at the end of the talk, so I'm just going to skip this. There's one more pattern, we're done. Visitor. So visitor was super complicated to implement in Java. In Ruby, I think it's a lot simpler, or at least in my experience, it was simpler to implement in Ruby than Java. But basically, there needs different ways of processing elements in an aggregate hierarchy to generate, for example, like generating, like you have a hierarchy of nodes, and you can use it to generate an HTML, or you can use it to generate SVG, like graphics, or you could do just HTML document. And so what you could do is build 2 visitors that will visit that hierarchy and then use an iterator. So this pattern, by the way, combines itself with the iterator pattern that we talked about earlier. It uses an iterator to move through that hierarchy, and then for every node, it visits it and generates something out of it. So if we're using an HTML visitor, then it'll take the node and maybe it'll read its text, and then it'll generate a div or a p, maybe like a p tag, and put the text in it. That's it. But if it's an SVG file, it's probably have to do something more complicated. SVGs do have support for rendering text, so it has to use the SVG way of rendering text. So it'll have a different implementation. So every visitor has its own implementation. So I used it again for a real thing. I used it in Glimmer DSL for XML, which is used in the web version that just won an award last month. Basically, this one will generate either XML or HTML from Glimmer syntax in Ruby. So from Ruby code, you can generate XML or HTML. I have an XML visitor and an HTML visitor. And they visit a hierarchy of basically nodes built out of the DSL. I'll show you what I'm talking about. So actually, this is just the visitor itself. So that's an XML visitor. So when it's visiting nodes, if there are children, it does something, and then does something after the children, and it opens a tag here, and it ends a tag here. It basically generates XML, and it's doing it gradually in the visitor. And then I have, let's go back here, and then there's an HTML one that is slightly different. The XML rules are slightly different from the HTML rules. The HTML one is a bit simpler, but basically they'll visit what I showed you earlier here. So here, so like let's just say I opened here. Let's look at, sorry, here. Okay, here I have a hierarchy of, let me go with something simpler. Form is good. Okay, there you go. So I have div with an h1, a form, a div, etc. So we have here Ruby code that's generating a hierarchy of elements in that could be generated as HTML or XML. Normally you want this to be HTML because it is HTML, but if I use the XML visitor, it's not going to check for the HTML syntax. It'll accept everything, because in XML you can generate any element with any name. So you can make something called car. I mean, HTML recently supported that with web components, but I'm not going to get into that. But HTML usually just has, specific keywords, like you have div, label, input, form, etc. XML lets you generate anything, so that's the point. That's the difference between those two visitors. That's why the XML one was more complicated, but basically it takes this hierarchy that's built in Ruby and it generates HTML from it. And then it gives us this basically. This is the real HTML that came out of it. It even includes like validation rules, stuff like that. But yeah, there we go. So that is it. Design patterns are amazing. So what are some alternative implementations? I mean, this is just the final page in this final slide in the talk. What are some alternative implementations to design patterns in Ruby? So like back in Java and C++, you had to create objects for everything. Ruby lets you create blocks or procs, and procs are objects. Even methods in Ruby are objects. They could be treated as procs. So in Ruby, you don't have to actually, if I have command pattern, I don't have to create command objects if I don't need them. If I don't need undo, for example, I will always have a call, like just a call. I'll only be calling the command logic. In that case, I can just use Ruby blocks directly and basically bypass the creation of objects and write less code. So Ruby gives us those options, like strategy pattern. For example, if I have 3 strategies, like for credit card, ACH, debit, and something else, Apple Pay, you can take 3 blocks and put them in a hash and then give them strategy names and in one file. And if the code is super like small, like it's just, if the whole code of all those 3 strategies was like 10 lines of code, there's no point of creating 3 different classes for them outside the file. It's a waste of time. So Ruby gives you more flexibility in writing even less code and being more agile, basically, by using Ruby blocks. State is the same way. I can enumerate the states. If the states were very simple and they didn't have many methods, or they only had one method, I mean, that happens sometimes. Then you can just enumerate the states as blocks within a hash that has the state names as keys, and that's it. You don't need to build classes for them. But if they do have multiple methods for each state, then that doesn't work anymore. Then it's better to build classes in that case. So decorator, adapter, proxy, those can be handled in different ways. Like in Ruby, if you use method missing, you can have an object take another object in the constructor and save it, and then use method missing to delegate all the work to the other object. Now that's not the safe recommended way of doing it, so I don't recommend it, but it's just one way of doing it. The more recommended way is to use a class like forwardable or delegator that come with Ruby or Rails as libraries, and they let you basically quickly implement the decorator, adapter, and proxy patterns. Template method and factory method often in Java or C++ need abstract methods, which are called hook methods. In Ruby, you can use the abstract library to build abstract methods if you want. But one thing I forgot to put in the slides is you don't need that too as well. If you want, you could just do what I was showing you in the code. You would just write raise not implemented, and that's the signal that the subclass has to implement that method, and then the subclass can later implement it. But if you want to do the Java way, you would use the abstract library and you would designate a method as abstract, and that makes Ruby do almost the same thing as raise not implemented automatically, though, without you writing that code. The abstract factory can use that library as well, or raise errors for methods that need implementation. That's about it. So to review, we went through a pop quiz at first about who the gang of 4 are, and then we talked about what a design pattern is, and then what it consists of, and then what are the categories of design patterns. And then finally, we went through design pattern benefits, and finally we jumped into practical applications of design patterns in Ruby, and alternative implementations for some of the design patterns in Ruby. And as far as resources that I recommend the Design Patterns book by the Gang of 4, which was the original book that introduced design patterns. Then there's the Head First Design Patterns modern book, which came out in the 2000s for the first version and in the 2010s for the newer version. That's a very easy to read book. This book is a bit like, it's very technical. Like you have to read very technical language in this. This one is more like, it has a very casual language. It's good to have both, honestly. I like both books. I like this book quite a bit, but this book also has very good examples for how do you apply design patterns in practice. So I recommend both. And as a resource online, there's this Refactoring Guru website, which has very nice graphics for illustrating design patterns. I think I have it open here somewhere. Probably here. Yeah, there it is. So for example, what pattern is this? Let me see. Is that bridge? No. Oh, that's decorator. That's pretty cool. Yeah, they have very cool graphics that explain things. Like, see, I have an object. I just decorated it with this. But then you can put a decorator on the decorator. I showed you that in the code. That's a very, very good like graphic that illustrates it. Like you can put a decorator on the decorator on the decorator. Decorate, like have any combination decorators that you want. So yeah, and it gives you some diagrams. It gives you some examples. And it's a bit, this website gives you more modern examples. Let me see what language they use. I don't remember. I'm not sure what this language is. Can you guys tell? It would be funny if it's just pseudocode. Maybe that's what it is.
Probably is, yeah. No, that's not Java.
It said method. Java doesn't have method in it, like just method as a keyword.
It doesn't have end.
Right. But yeah, otherwise, that's my GitHub. If you want to check out my projects. I did create a project that has most of the examples that are illustrated in the slides. But honestly, most of the code that I created doesn't have a real implementation in it. It's just like fluff, like just to show you the structure. The structure is what matters, not the implementation. But I created a whole bunch of examples here. So I'm going to post them on GitHub. So if you monitor my GitHub, you'll find them. They're going to be under a repo called Design Patterns in Ruby. So yeah, that's it. Thank you, everyone.